Okay, so I'm going to keep the slides short today, and the whole thing will probably be relatively short. I know it's the end of the day there as well. So turboSETI is a code that does what's called a Doppler drift search. So the Earth is not, well, depending what you believe. If you don't believe in the flat Earth, the Earth is a sphere and or oblate spheroid, and it's spinning in space and it's going around the sun. That means that anything that isn't fixed on the surface of the Earth will have some kind of Doppler effect added to it due to the relative motion between the Earth and it. So for example, if you're looking at a satellite, you don't expect to see the satellite at its native frequency that's outputting at. You expect a small difference in the actual observed frequency because of it's moving. Just how when a car is moving and you hear the sound of the siren or the ambulance, whatever, change, but you hear the Doppler effect. Sorry, it is early in the morning here, so my explanations may be a bit poor. An interesting thing about satellites, as an aside, for GPS, it's not just the Doppler effect that you have to take into account. If you want to know where you are on the surface of the Earth, you actually, the motion of those satellites actually is also affected by gravity, essentially. You have to use special relativity to fix the time of arrivals because they're moving and because of gravity and stuff. So we don't have to worry about that with just detecting a signal, but things are always a little bit more complicated when you have multiple rest frames and such. So I won't go too far into the math, and it's pretty simple math. In the scheme of things, if you have a receiver fixed on Earth, any transmitter that's not on the Earth's surface will have a time-dependent Doppler shift. So the maximum you expect depends on the, just this delta V, the relative velocity over the speed of light. For short durations, so most of the breathedness and observation we've been doing the Green Bank and Parks are 5 minutes. This is just well approximated by a linear function, so you've just got the frequency naught, and then V dot is just the shift in frequency that's measured in hertz per second. So you'll hear us talk about hertz per second for Doppler drift. The only other thing that I'll say is that the size of the hertz per second, the size of the search space, depends on how fast you expect planets to spin. And there's some pretty interesting, if anyone's working with Sophia, or if you get a chance to talk with her, she's done some calculations on these that are pretty fun. So in terms of Earth, Earth is spinning. We expect the daily rotation gives you a drift rate of at about 1 gigahertz up to 0.38 hertz per second. So this is not a huge effect. We can measure it in our data because we have such fine resolution. But other data products, like if you were just looking for spectral lines in space, you wouldn't really notice this effect all that much.
Sorry, Danny, just to interject, Sophia's going to give us a talk next week, actually, in more depth about her recent paper in calculating these drift rates.
Oh, great. Well, I won't go too far into this then. I'll just show you the formula. There's this 4 pi squared, which all good formulas should have a 4 and a pi in it. R is the radius of something, so then with the radius of Earth. Nu naught is the rest frequency. C is speed of light, and P squared is the rotational period. Sorry, yeah. So how long it takes to do an orbit. So the main thing to note here is that in terms of Earth, we're spinning like this, and then we're going around the sun as well. The going around the sun doesn't make that big of a difference in terms of the how much the Doppler drift changes as a function of time. It will impart a kind of a more static component, though, of course. So in terms of fun numbers, one of the things Sophia did was say, if you have a rocky planet, how fast can it spin until it would literally just explode because it's spinning so fast. And that gives you a kind of maximum that you could possibly ever expect for New York. And I think she came up with a couple of hundred hertz per second for that. For most what we think are sane numbers, it's about plus or minus a hertz a second for the search that you'd want to do for a rocky planet that's at a reasonable orbit, putting in reasonable numbers. As soon as you put a satellite around the planet or a moon around a planet, those numbers can go up though. So we've generally searched plus or minus 2 hertz a second. Sophia's arguing for higher rates than that. Anyway, that's the only bit of math background I wanted to give. So I will stop the share, and now I will go to the next part, which is just playing around in real time with the software and hoping it works. Any questions at this point? Okay, so the turboSETI software is written in Python, and the actual Doppler bit is written in something called Cython, which is this weird mix of Python and C. And it's just an algorithm that takes into account the drift and adds up things so that you get a higher signal to noise. It has a GitHub page, which is on the UC Berkeley GitHub, which we can share if you need it. And you can see that there's some files in here. It does now have a website, which is kind of new, which has some documentation on the API, the interface to all the methods, but it is still wanting in terms of documentation. So you can see there's some information about the different things you can run on it, but it doesn't give you a kind of nice hand-holding, this is a tutorial and this is what you do.
One of you should write that tutorial this summer.
Okay, so I have a little notebook that I can go through to show you about this. So let's see, everyone can see my screen, right? So first thing I do in that thing is make sure that the plots are inside the notebook so everyone can see them. One thing I've done already is I downloaded some data from Voyager. And then I've got my import. So this is the magic line for turboSETI. I'm also importing pandas, which is for using, if you have tables of data, pandas is really good. NumPy is if you have arrays of data. PyLab is for plotting, it's matplotlib. TurboSETI OS is just so I could download the file, and then Blimpy. So Blimpy was so I could show you what was in the file. So the file has some data in it at 8 gigahertz, and the channel size is 2.79 hertz. And there's some other information here. So we looked at this, when we looked at it, Voyager was at this declination. And we use Greenbank. So this telescope ID is terrible, but 6 is Greenbank. We integrated for 18 seconds, and this was done back in 2016 in September. Okay, and so turboSETI has this thing called find Doppler, which is the main thing that you'll want to run. The doc string, I'll take you through all of these things. The first thing is you need to give it a data file. Second is you need to give it a drift rate to search. Third, you need a signal to noise ratio. So the lowest you can set the signal to noise ratio to, well, I guess in theory is 1, but you would very rarely run this under 10. You find if you think of noise, so Gaussian-like noise, you just have, essentially some kind of random process. Every now and again, you'll get an outlier that is just a much bigger number than general if you have a Gaussian process. And if you set the signal to noise low, you'll find that you just have all of these outliers that are just due to random chance. So generally, you set the signal to noise ratio to somewhere, well, 10 is a good ballpark, and you wouldn't expect to find many outliers just due to random processes. Then you have where you want to output things to, a list of cross channels if you need this obs info dict, which probably deprecate because it's kind of confusing. And that was because this is still code that gets used for and abused in different ways, different projects, some flagging options, and some other things about cross channels. So the easiest way, this is kind of a short example, is you make a fine Doppler instance by doing the data file. So this we're using Voyager. We're going to search from a maximum drift of 1 and a minimum drift of 0, signal noise of 10, and output to the current directory. So let's run the search. How do you do this? I haven't used timing magic for a while. So searches are still pretty slow. They search all of the data and they do a variety of different, well, that didn't work. Oh, wow. Welcome to production code. So maybe I'm in the wrong directory or something. I did run this before everyone got here and it was working, but of course it's not now. Okay, so I may have just been in the wrong directory. So that took a few seconds to run. This is on one channel, one course channel, so a couple of megahertz of data. And so when I did the search, it made an output file, which is in a DAT format. So let's have a look here at the files. So it made two files. One is called .log, and let's have a quick look at the log. And you see just some kind of diagnostic information about these hits that things it found. You probably won't need to look at this too much, but at the bottom you can see it found 3 hits that it thinks are really good. One at 30 signal to noise, 245, and 31. We look at this .dat file. It has a header here, and then after the header, and you can't really read it because it's in it. Let's make my browser a bit bigger. You can see at the bottom it has some information about the hit, so top hit, drift rate, signal to noise, and some other stuff. So you can read this with turboSETI. But let's just try from scratch. So I'm going to delete these files and make sure that they get made again. So delete. Go back to here. I'm going to run this thing again. And you see it just made 2 things out there. So it's working on the files. There we go. Okay. So I made a DAT file and the log file. I'm going to load the DAT file using a function in turboSETI, which we just load it into a pandas data frame. So if we do type of DAT, it's a pandas data frame. And in here, you can see there's 3 hits, all around the same drift rate, about minus 0.39. Signal to noise, the frequency, channel index, start frequency, course channel number, and some other diagnostic stuff. So the source, the MDAG, RA, DEC, the time, and the frequency resolution. So there is a function called plot hit, which will allow you to plot some of the data in this file. So let's give that a go. So you give it it has to know the name of the file and also the name of the data file. the DAT file, and the index of the hit that you want to run. So in this example, we found 3 hits, and so that's easy to go through by hand and look at. But often you will find a lot more than 3. You'll find millions of hits if the RFI is bad. RFI is radio frequency interference. So if the RFI is bad, then you probably won't want to go through and look at every single hit by eye. Let's look at another one. So this one, I'm looking at the second hit, and I put in an offset of 100 hertz. So this red line, this dotted line of what it thinks a drift is, doesn't lie directly over it. And so if I put in an offset of 200 hertz to move it more to the side, so it's more over here now, and so just showing it. So these are things that it thinks could be alien signals, but this is obviously the Voyager telescope. So we can do the third and final hit that it came up with. Oh, sorry, there's only indexing error there. So you'll see that here it thinks that this one is the actual hit, this one is not the actual hit. Because these are so close together, it will only count these as one hit. And this one was slightly stronger signal to noise, just due to the observation. You can also see, like over here, there's probably a bit of a hit over here as well, which doesn't show up because this one dominates. So we could have also looked for these manually. So here is the file. So you can do a.plot waterfall. I'm going to manually set the f-start to be 8419.2742. I'm just reading this off the plot up there. F-stop equals 8419.2744. Let's see if, and there you can see the data's in there. And so if you wanted to look a bit broader, you could change this. So you see, if you look really broadly, this is over a megahertz, which in the scheme of things isn't that much bandwidth. You can't see the plot at all. You can't see that line. So you really have to be close. So this is kind of one of the issues with SETI is data's really big and you can't really visualize it very well. Often you have to be very careful because you can't fit billions of points on your screen. And so you can very easily miss a signal. So that's kind of the basics of turboSETI. I don't have too much more to say apart from if you're using it, please help us document it and improve the quality and whatnot. Yeah.
Cool. Thanks, Danny. Questions for Danny?
Just kind of a general question, but like, how do you like actually computationally calculate the drift rate of a signal? Since, you know, first you need to detect the signal, then you need to actually calculate the actual drift, which is, you know, less than trivial by then if you actually detect that signal, I guess. But yeah.
Yeah, so the actual algorithm is called a Taylor tree style algorithm, and it's kind of similar to an FFT, where a fast Fourier transform, where it reuses parts of the calculation. The simplest way of thinking of it, if you wanted to do this manually, you have kind of an array, and in your array you have some kind of thing going through it diagonally. You would figure out what kind of shift you need. So if you know you're looking for 1 hertz a second and your time resolution is 1 hertz, then on the second integration you have to shift that by a hertz. The third integration you have to shift that by 2 hertz, and so on. If your time integration was 10 seconds, then you'd have to do things differently. So you'd have to shift the first integration by 10 seconds, sorry, by 10 hertz instead. So the actual algorithm, like if you wanted to do it manually, you just kind of figure out how to line everything up based on the drift rate you're searching. because you search multiple drift rates, if you wanted, depends on the kind of resolution of your drift search. But if you wanted to search from 0 to 1, you might, for example, search by 0.1 hertz. So shift it by 0.1 hertz, line everything up, and then you take the sum or the mean down the time axis, so you just get one spectrum out, and then you see if anything's above your signal to noise threshold. Then you do it again for the next one. So you go to 0.2 hertz, and then shift everything, sum over the axis, and then look for things above the threshold.
Yeah, so it's like basically de-dispersion for instead, but for like frequency by frequency, right?
It is exactly de-dispersion. If you were to set the frequency law, instead of having frequency to the power -2. So de-dispersion is something that you do on pulsars. So just for everyone, pulsars, when they travel through space, pulsars themselves actually output kind of these nanosecond or millisecond pulses. So they're like lighthouses spinning in space. Star explodes, you're left with the neutron star. And these things have incredibly strong magnetic fields, and they have these kind of jets of radio emission coming out of them that are kind of forced out by the magnetic fields to go on these two axes. And so it spins around like a lighthouse. If you happen to be in the line of a pulsar as it goes past, you'll see a blip when it goes past. So you see your energy go up. And it's a very broadband thing. So it will go across your entire band. And so when you see that, the signal is actually de-dispersed because it has to travel through space. Sorry, it's dispersed because it travels through space. So that means that as it travels through space, some frequencies arrive before other frequencies because they're delayed by having to travel through the interstellar medium. So essentially, there's electrons in the way, and those electrons make longer frequencies take a little bit longer to get to you. So you see this characteristic kind of frequency chirp. Looks like Steve's about to, or someone's about to share something. And this is kind of a curved line. And the curve that you see is due to the physics of dispersion, and that's a frequency to the -2. With Doppler drifts, the things that we expect from the Earth's rotation on short time periods, it's just a linear chirp that you see instead of this parabolic kind of chirp.
So I spent a few minutes going over this in a talk that I did not earlier this week, but at a meeting where I was talking about Doppler drift searches, and I think, you know, for me, kind of thinking about this in sort of a visual sense sort of helped. And here's an example where it's kind of very pixelated of a drifting signal, where I'm assuming each of these squares is 1 hertz in frequency on the horizontal axis and then 1 second in time on the vertical axis. And I've got a signal going through, which is the orange line, which you can see is drifting by 2 hertz every second. And it's kind of lighting up those red squares basically as it's going through them. So it's a little bit kind of contrived, but you know, for a signal that's drifting at exactly 2 hertz a second, that's the kind of thing that you would see in your spectrogram. And so what you have down at the bottom is basically you're summing up each column, and you see you're counting the number of red squares that are in each column there, and you see there's some zeros at the left-hand side here until you get along to the first one with a red square. Okay, we're counting this up. We've got 1 down at the bottom, then the next one, we're counting this up. We've got 1 red square, and then you move along to the next one, 1 red square, and so on. And then if I try, okay, well, let's just kind of, you know, move everything along a little bit and then add them up again. So again, here's my 2 hertz signal, but now I've kind of shifted the array basically by 1 step on each row, and I'm summing up again, and I get a bunch of zeros, and then I get a 1, and then I get a 2 here, and then I get another 2 here, and so on. I'm doing better. I'm getting closer. You know, I'm getting closer to what the true drift rate is. And then I shift each row again by 2, is what I'm showing here. And I'm adding everything up, 0, 0, 0, 0, 0, and then I get a 7 and a 7 here, which corresponds to this 2 hertz per second shift. So maybe this kind of helps sort of visualize basically here that was the true drift rate. Now I've maximized basically the signal that's down at the bottom here. So again, going back And that's what it was originally. I've tried 1 hertz per second and summed it up, and then I've tried 2 hertz per second and summed it up, and 2 hertz per second is the correct answer basically here for this drifting signal. The one thing that's a little bit different to how this is implemented in practice basically is the fact that we can take advantage of the fact that with a small shift like that, you don't have to do some of the calculations for kind of the first rows again, basically, because, and this is a little bit kind of harder to wrap your head around, but the sort of redundant calculations with shifts that are sort of too small to make a difference to the overall calculations. And you see here, basically, the ones at the bottom are moving more than the ones at the top. Sorry. Like this one ends up over here. This one only ends up over here. So, I need to do more calculations down here because this is basically moving faster as I'm kind of doing the D drift calculation here. Does that make any sense? Does it make more sense to make it more confusing? I don't know if this is helpful, but if you nod.
That helped.
Okay.
To finish, a side note in terms of, sorry?
Somebody else was asking, can I ask a question?
I have a question, you can go ahead.
Go ahead.
To finish off the side note, with pulsar searches, they generally, well, to date, haven't used tree-based searches. They've done a brute force search. So with GPUs, when they came out, they found that they could just do a really hard brute force search and try every single dispersion measure they could think of, throw it at the problem, see which one gives you the highest signal to noise ratio. There is now something called the fast dispersion measure transform, which is if you set the scaling law to, instead of using a parabolic, use a linear chirp, it is identical to the thing that we're using.